Good morning, everyone. We'll start the presentation by defining terms that are related to sensors. From then, we'll explain what a load cell is and what it does. We will also explain how the strain gauge works and describe the main features of the strain gauge. We will discuss two assembly processes, moment and temperature compensation, that are performed on load cells in order to enhance the performance. We will discuss what a calibration run consists of and explain the performance parameters that need to be met by the sensor. We'll take a look at a typical interface specification sheet and show you where the performance parameters that have been discussed throughout the presentation can be located. We will also talk about some of the industries where load cells are used, and we end up concluding the presentation with a question and answer segment. So let's go over some definitions. First, axial load. The axial load is a force that is applied along the center axis of the sensor. Calibration is a testing of the sensor to verify that it meets performance specifications. The capacity refers to the maximum axial load or force a sensor is designed to measure and still meet performance specifications. The deflection is the deformation of the sensor under a force. The eccentric load is a load that is parallel to the axis of the sensor, but unlike the axial load, it is not concentric to the center axis of the sensor. Next, non-linearity, hysteresis, and SEB are some of the performance parameters that the sensor is tested for. But unlike some of the other performance parameters, let's say like symmetry, repeatability, and creep, these three parameters, non-linearity, hysteresis, and SEB, those are recorded on a standard calibration form. The output is the electrical signal coming out of the sensor. And last, the rated output is the electrical signal coming out of that sensor at capacity. And if you would like a more detailed list of definitions or terms, please go to our website where you can find one there. And now to explain what the load cell is, let me hand this over to Jack.
All right, good morning, everybody. What is a load cell? A load cell is a device that converts a force into an electrical signal. Of course, they're designed to measure loads, tension, or compression, or both, which we would call universal within the industry. There are no moving parts, and this allows for the lack of wear and tear between any main components. Then moving on, let's see, types of load cells. Now, oftentimes, the type of load cell will be decided using the customer's constraints, more or less. Oftentimes, a customer will have a certain accuracy requirement. Perhaps they're using it within a hazardous environment. Dimensional constraints are common constraints that I see within my daily work. And then capacity is also relevant, cost, and then the type of loading, how many cycles are going to be performed with this load cell, and will it need to be fatigue rated. All that being said, let's get into these types of load cells. First is the bending beam. Right here is our MB type, or MB bending beam type load cell, popular within lab and medical environments. Next is below that the dual bending beam. This is an SML, or low height dual bending beam load cell. It allows for a center mounting thread, and it's also got overload protection. And then on the right there is a column style load cell. Column style load cells are popular, most popular within test stands in my experience. They're convenient in that they offer a high rated capacity with a smaller diameter where a low profile may not fit. All right, moving on to the next slide. Starting from the left going right, that's our S-type load cell. It's also got a center mounting thread. It's got great accuracy for a low cost. Below that is our SMT. This is also an S-type load cell, but it offers overload protection in both tension and compression. So for those applications where you foresee, a force or a load going past, unintentionally, what you would expect, then this would be a perfect option. And then last but not least, a load button. Load buttons are extremely popular for those applications that are restricted in space, and this obviously is a compression-only load cell. So they are great for smaller spots. Squeeze it in. And then moving on, the anatomy of a low-profile load cell. Now, the low-profile load cell is certainly our flagship product. It is our most popular product by far, hands down. Starting from the top going down, the hub is the center of the load cell. It's got the center mounting threads, and this is where you would mount from the top, and from the bottom there's a thread that matches on the base. Next is the strain gauge. This is the element or the resistor which takes the strain and converts the force into an electrical signal. Next are the interconnecting wires. These wires connect the strain gauge to the external connector that you see on the far left. Next is the base. The base is critical for two reasons. Number one, it offers a specific hardness, typically 31 to 33 Rockwell C, and then it also offers a certain flatness specification, to be specific, 2/10,000ths of an inch. And that's incredibly flat. And so it's these two combined features that allow us to support the specifications that we provide on our data sheets. And then is the diaphragm. The diaphragm is often found on both the top and the bottom, and this offers protection against any contaminants from getting inside. And then again is the connector on the left, and this is where the interconnect wires from the internal come outside, and where you connect the mating connector to bring to your data acquisition or whatever kind of instrumentation you would be using. And now I will send it back over to Albert for main components.
Thank you, Jack.
We're having a little bit of technical difficulties, so when it says that Jack is speaking, Albert's computer just died, so it might be Albert. Just a heads up. Back to you, Albert.
Thank you, Nikki. So continuing on with the anatomy of the load cell, let me talk about its two main components. First, we have the flexure, which is the load-bearing component of the sensor, and sections along the flexure are designed to deform under load. The second component is the strain gauge. The strain gauge measures the magnitude of the deformations in the flexure. The deformations in a flexure cause the strain gauge to change its resistance. When we arrange several strain gauge in a particular pattern, we get what is called a Wheatstone Bridge, and it's what causes, or I should say, it is the deformations occurring along the flexure that cause the resistance across the Wheatstone Bridge to change, and therefore the output signal coming out of the load cell is able to change as well. Now, let's talk a little bit about flexure design. So when a new application, or depending on the capacity that the sensor is meant to withstand, we look at three different materials. We use aluminum 2024, We use E4340 steel and 17-4 stainless steel. 2024 aluminum is typically used for capacities of 3,000 pounds and lower. E4340 steel is used for capacities of 5,000 pounds and higher, and stainless steel is typically used for submersible, hermetic, or for corrosive environment applications. One of the features that we look into when designing our flexures are the dimensions of the beams, particularly the thickness and the height of the beams. Those beams are designed to deform under load to a specific strain value. It is along the beams where the stress occurring in the flexure concentrate, and therefore those are the prime locations for bonding the strain gauge to a flexure. Moving on, let's talk a little bit about the strain gauge. Here we have an image of the basic features of a strain gauge. Number one is pointing to the grid lines, which are the strain sensitive pattern that measures the magnitude of the deformations along the flexure. Number two points to the end loops. The end loops are designed to particular dimensions in order to provide for creep compensation. Number three are the solder pads where electrical connections are made. The fiducials, these assist during gauge bonding in order to align the gauge correctly along the beams. Number five is a backing, which is the material that prevents contact between the foil material and the flexure, and it is where the adhesive is placed in order to bond the strain gauge to the flexure component. Here we have 4 different images showing some of the typical strain gauges that we use here at Interface. The first one is a linear type, which is what you would typically find in bending type applications. The second image is that of a shear gauge, which is what we use on a pancake or low profile type strain gauge. The third image is that of a pulse-on gauge, which measures strains that occur along the center axis of the locel and also deformations occurring perpendicular to the center axis of the locel. The last image is that of a chevron type strain gauge, which is typically used for torsion applications, and it's what you would typically find on some of our 5400 series transducers. Now let's go into a little bit more of a detail of what the Wheatstone Bridge is. So the typical arrangement of the bridge, in a typical arrangement, you will find 4 gauges, and in order for us to change the characteristics of the electrical signal coming out of the sensor, 2 of those gauges need to be in tension, and the other 2 need to be in compression. Those gauges in tension, there's an increased resistance across the gauges, and therefore the electrical current through them decreases. And in the case of the compression gauges, the electrical resistance decreases, and therefore you have a bigger rate of electrical flow across those gauges. So how do those electrical, or how do the resistance changes across a gauge? So if we take a wire element and we pull on it on the ends, what we have is the condition where the cross-sectional area of that wire element decreases, therefore decreasing the current flow across it. And what this causes is an increased electrical resistance. If on the other hand, instead of pulling on the ends, but in this case, if we were to imagine us pulling from the sides of this wire element, what we cause is an increase in the cross-sectional area of this wire segment. What this does, it increases the current flow across that segment of wire, and therefore the electrical resistance decreases. Now let's talk about how the flexure element causes causes that resistance to change across the gauge. In this image, we have the cross-sectional view of a low-profile sensor, and highlighted in blue are the sections where the strain gauges are bonded to. In this case, there is no load being applied yet, but if we move on to the next slide and we apply a tension load, we can see that those beams are deforming. And now what we have inside those blue boxes, represented by the red lines, are strains. Some of those strains cause gauges to be under tension, and some of those strains cause the strain gauge on the opposite side to be under compression. If we move over to the next slide, we focus on the region that is in tension, we can see that when the strain gauge, or I should say when the grid lines on the strain gauge align with the strains occurring along the beams, the gauge is under tension, and therefore the electrical resistance across that gauge increases. If we take that same gauge and we place it on the opposite end, we can see that the grid lines are now perpendicular to the strains along the beams. And in this case, the gauge is under compression, and therefore the resistance across that gauge decreases. And this is how it is possible to change the resistance across identical gauges that are installed on the same flexure. Now we talk about the pancake style, how the strains occur along the beams. In this video, we can see how a bending beam flexure works when a load is applied to one end. As you can see, the regions that are changing in color is where the stresses or the strains are concentrating, and those would be the ideal locations for gauge bonding. Now, if we take a look at this next image, we can see again that in a typical Wheatstone bridge with a 4-gauge arrangement, 2 of those strain gauges will be in compression and 2 of those gauges will be under tension, and therefore allowing us to vary the electrical signal coming out of the sensor. And now to explain why we make our own strain gauges here at interface, here's Jack.
All right, thank you, Albert. All right, you can see why do we make our own strain gauges? Proprietary interfaced foil strain gauges are thermally matched to the load cell material. As a result, our load cells do not require modulus compensation resistors. More or less, we thermally match the properties of the gauge material to the material to which the gauge is being mounted, or in other words, the flexure element. As it mentions, as a result, we do not require modulus compensation resistors. This is one less component that could prove to be a faulty or a deterrent to a properly functioning load cell. And then this allows for far superior temperature performance along with higher output. Typically 4 millivolts per volt, at lower mechanical strain levels, which is optimal within the force measurement industry. Higher output means higher resolution and better signal-to-noise ratio. All right, moment compensation. Moment compensation, it says it reduces force measurement errors due to eccentric loads. And it does just that. It doesn't eliminate any influence of side loads or off-axis loading. However, it works to minimize these potential errors within the output signal. And this is performed by loading the cell eccentrically. So allowing a torque arm to be mounted at the top of our low-profile load cells. Now, this is done to every one of our low-profile load cells, and this is certainly one of the most significant or noteworthy features of our low-profile load cells. You can see the torque arm there in the photo, and there's a weight hanging on top of that torque arm. This allows for, the moment to be induced, and then as we rotate, we compensate going around the load cell.
So in this next slide, we show the typical signal characteristic of a sensor that has not been moment compensated, along with the same output signal. However, in this case, when the sensor has been compensated. So as we can see in the case of the uncompensated load cell, the error induced into the output signal can be as high as 0.80% in this case. However, after moment compensation is performed, that error reduces down to 0.17% and allowing this sensor to meet our moment performance specification of 0.25%. Now, why do we perform temperature compensation? We do this in order to maintain the zero balance of the sensor within performance specifications. These errors, the temperature errors are induced into the signal in the case where the temperature is changing, the ambient temperature is changing, and we have a zero output that is changing as the temperature increases or decreases. We typically perform this test from temperatures going down from 15 degrees all the way up to 150 degrees Fahrenheit. And as mentioned previously, the test is performed in a no load condition or no load applied to the sensor. Once the test is performed, we determine how much compensating wire we need to add, and we need to add to the circuit in order to minimize the error. In this next slide, we can see the improvements made to a sensor after it has been compensated. Here we show 3 different graphs, one for the uncompensated case. The blue line is for the compensated case where it takes place from room temperature all the way up to a hot temperature. And the third case, represented by the green graph, is where the compensation takes place from cold to hot to a hot temperature. As you can see, represented by the red graph, the error of the zero balance reading can be all the way up to 12 pounds. In the second case, where the compensation takes place from room to hot, it is further reduced. The error is further reduced. However, instead of being 12 pounds, it's now decreased by less than half. In this case, just under 6 pounds. But if we perform this temperature compensation from cold to hot, the amount of error is much further reduced, and in this case, it goes down to just less than 4 pounds. And now to talk a little bit about calibration, I'm going to hand this over to Jack.
Thank you, sir. All right, calibration. Calibration is performed to verify the load cell meets performance parameters, more or less to characterize a load cell's performance and ensure that it is meeting performance criteria. Now, every load cell that goes out of our door comes with a niche traceable cert at the very least. We also offer A2LA or ISO 17025 calibrations, as well as ASTM E74 compliant calibrations. Something to note is that Interface offers recalibration services for any manufacturer of load cells, so that is something to keep in mind.
So I have talked about nonlinearity, hysteresis, and SEB, but haven't really explained what these are. So as we can see here, this is a typical calibration run, and it is performed, a typical calibration is performed in a 5 up, 1 down run. And what I mean by that is that we take on the ascending direction, we take a reading at 20, at 40, at 60, and at 80, and also at 100% of the rated load. And then on the descending direction, we take another reading at the 40% value. In order to determine the nonlinearity, we measure the errors of the ascending values and compare those to the best fit straight line that is drawn through 0 and to the reading at capacity, and determine what the nonlinear, and compare those numbers to the best fit line and determine what the nonlinearity error is. The hysteresis, we take the difference between the results taken at 40% in the ascending and descending runs in order to determine what the hysteresis error is. The SEB, or the static error band, is a band of maximum deviations of the ascending and descending calibration points from a best fit line through 0 output. It includes the effects of nonlinearity and hysteresis, and also the non-return to minimum load. And now that we have explained what some of these performance parameters are, and some of the previous ones, as in the case of temp, comp, and moment, what we have here is a typical interface specification sheet. Towards the top, highlighted in yellow, we can see there where you can find these, the maximum value of the errors associated with either of those parameters. On the very top, we have the SEB. Right below that, we have the nonlinearity and hysteresis. More towards, if you go towards the electrical, if I'm not mistaken, sorry, under temperature, we can see there the maximum error associated with the temperature effect on 0 balance. And towards the bottom, we can also highlight in yellow, we can see some of the maximum deflections that load cells are designed to withstand.
Okay, so that wraps up the first part of our presentation. Before we get into some application-specific uses for load cells, I'm going to go ahead and launch our second poll. Enjoy our little keyboard cat and dancing with the gopher. Groundhog. It's not quite Groundhog's Day. So the question is, what industry do you work in? If it's not up there, just pick your closest, or you can go ahead and pass on this poll. While you're answering that, I wanted to mention there is a free handout available to everybody in attendee. So in your GoToWebinar panel under handouts, you should see the ability to download the LCFG, that stands for Load Cell Field Guide, Chapter 1 promo. That is the Load Cell 101 document that was combined into our Load Cell Field Guide, which is available for purchase on Amazon, or if you can get a hold of one of the interface reps. Typically they have a couple copies. And I wanted to put out my email, go2@interfaceforce.com, if you have any questions about the webinar today, if we don't get to your question later. And right now I'd like to start opening it up for Q&A before we go into the application. So if you have any questions about the material that we've gone over today, please enter that into the questions field so we can start getting that. Oh, I'm going to close this poll. Thank you so much, and I'm going to pass it back to Jack, who's going to talk about some materials testing applications.
All right, a very common application for our load cells are material testing machines. A lot of these machines are doing fatigue testing, basically breaking the specimen. In this photo you see a tensile testing machine. Now I've seen tests ranging from tensile tests of fasteners, so hardware, hex head cap screws for example, to fatigue testing of fabrics for ropes. And you can imagine cargo ropes need to be specified at a certain braking force. So that is another common application. Also commonly used, these load cells are used in compression as well, and you can imagine that customers will be measuring the braking force of materials such as concrete, plastics, or foams, for safety reasons. Moving on to the next application, you can see here a video showing the flex and strain of the wings of an aircraft. So this is airframe validation. It's performed to ensure structural integrity of the aircraft's components. I am told by Albert, who had the pleasure to attend one of these testing scenarios live, that it's pretty frightening. In fact, you can hear the creaks and cracking of the elements under strain. So I can imagine that might be pretty frightening. But better to do it on the floor before we all get up into the air in one of these bad boys.
Okay, I'm going to actually take this application because I have had the pleasure of going down to Tucson to the now Richard F. Karras Mirror Lab. It sits underneath the football stadium at the U of A, and they make giant telescope mirrors. And what we're looking at here is the polishing process that they use to get these mirrors accurate. 1/1000th over a 16-foot diameter. They're about 5 stories tall. So what you're looking at right here is a mirror that's being prepped for the Giant Magellan Telescope, which is under construction in northern Chile. The polishing process you can see in that inset mirror, they're actually using about 40 different beam load cells around the edges of that to maintain the force for the polish to get the perfect concave polish. So that's a really cool application. They also use load cells underneath the structures that balance these mirrors to make sure that they stay balanced and pointed in the right direction to capture the light just right. So that wraps up our well, we have a couple more. There's other applications for load cells. I'm sure all of you guys know this. I'll take this slide. So automotive, oil and gas and new energy, medical, industrial weighing and automation, and also we're seeing a lot more in robotics. They're using some smaller load cells in the robotics to manage joints and grip. So it's a really cool application.